everybody. We are in week 2 of differentiation. So by the end of this week, you should be able to find stationary points. You should be able to use the first derivative to identify the nature of the stationary points. You should be able to use the second derivative to identify the nature of the stationary points. And finally, you should be able to solve optimization problems using differentiation as the optimization tool. Okay, so we have seen that when a function or equation of the curve is given by y is equal to ax to the power of n, the dy by dx or the gradient function is given by n times a times x to the power of n minus 1. And we have also seen that if f of x is a function, gradient of the tangent to a curve at any point can be known as gradient of the function or the first derivative or the first differential of the function or f prime x or dy by dx or the rate of change of function. So we also saw that, let's move it. We also saw the increasing and decreasing function. In the lecture, we solved a problem and you try to choose some points which are in that region. Yeah, that is, a function is increasing when the first derivative is greater than 0 at that point. A function is decreasing when f prime x is less than 0 at that point. That is, we took an example and we saw that at any point here, the function is increasing. And at any point here, the function is increasing, while here the function is decreasing. So that is your, sorry, that is your maximum value and that is your minimum value. So anywhere here it's decreasing. Yeah, so we have seen that, but let's do an example to understand that further. Okay, so let me take an example, like let's take the curve y is equal to x cube, and let's take any 2 points a and b, where a is 2 comma 8 and b is x comma y. That's b is any point. Yeah, this is a fixed point 2 comma 8 a, and I'm taking b as any fixed point. Now I'm going to move this point b towards a. So let's see what happens when we move this point b towards a. Yeah, so the gradient of this function will be the differentiation, first differentiation of this function. Yeah, so 3x squared. And at the point A, this fixed point 2 comma 8, at point A, what is the gradient? Dy by dx is equal to, substitute the value of x. Yeah, and then you get 12. So the gradient is 12. So at this point, the gradient is, at this point, the gradient is 12. Now, let's try to find the gradient by bringing the point closer. Okay, so let's say x, the point b, x is 2.1. Yeah, we are only considering the value of x, and then we substitute this value in the equation of the curve to find the value of y. Okay, so we can get, so we get the coordinate, the point itself. Yeah, so we're going to change the value of x such that x is getting closer and closer to a, that is 2. That is, the point B is getting closer and closer to A. Okay, so now x is 2.1. When x is 2.1, y is 9.261. And the gradient, substitute it here, and the gradient will be 12.61. You can either substitute there or you can say y1 minus y2 by x1 minus x2. Yeah, you know the formula of a line. The gradient of a line is y1 minus y2 or y2 minus 1, whatever you're taking, but do the same thing for the x. Yeah, okay, so use that and find the gradient of the line AB. Then bring it more closer and find the gradient. Then let's take that much closer. As you go closer and closer, what do you see? You're approaching the gradient 12, isn't it? So as B gets closer to A, the gradient approaches the value of 12. Yeah. So, and this value is the gradient of the tangent at that point A. Okay. So let's take an example now. Find the set of values of x for which the function is decreasing. So the question says you have to find the set of values of x. That is, you have to find the set of points where the function is decreasing. That means the gradient is negative. That means the first derivative should be less than 0. So we are given f of x. Now, first step would be to find the first derivative. Yeah. So let's first differentiate the function. And you get the first derivative, because 3x squared minus 4x plus x. Plus x is 1. The derivation of a constant is 0. So it's actually plus 0. Yeah. So we don't have to write 0. Okay. So we have differentiated it. We have to find where the function is decreasing now. Yes. That is, we have this condition where the gradient of the curve is negative. So we have 3x squared minus 4x plus 1 is less than 0. And you know that this is in the form of quadratics, isn't it? It's a quadratic equation, yeah, inequality here now. So you can factorize it and find the value of x where the gradient is going to be less than 0. So you're going to factorize that. And now you can say that x is less than 1 over 3 and x is less than 1. Got it? So when you solve this, you get x is less than 1 over 3 or x is less than 1. That means the function is decreasing between 1 over 3 and 1. Okay. Good. The set of values of x for which the function is decreasing. Okay. So let's now find the stationary points. The points where the gradient is equal to 0. So that means the gradient f prime x is equal to 0. Yeah. So there are 3 types of stationary points. One is the maximum, and the other one is the minimum point. That is a local maximum and a local minimum. And the third one is a point of inflection, which we do not include in the course. So you are going to concentrate only on the local maximum and local minimum. So a local maximum is a point where you have the function decreasing, that is the gradient is negative, and then it is 0, and then it starts increasing. That's what we're going to see now, yeah? And a local minimum is the gradient is increasing, that is, it is positive, and then it starts decreasing, negative, yeah? And at this point, that's what we're going to see, the gradient is going to be 0. So when a curve turns to create a local maximum, like this, or a local minimum, the gradient changes. That's what we're going to see now. For example, that's your local maximum and that's your local minimum. This is also sometimes known as turning point or stationary points, okay? So you can call them as turning points or stationary points when you're not sure whether it's a maximum or minimum point, yeah? So you know that it's a turning point, but what type of turning point? We don't know until you solve for it, yeah, or identify a way to see whether it's a maximum or minimum point. Okay, so maximum and minimum points can be called as turning points or stationary points. So when you move from left to right along the x direction, the gradient of the tangent is positive and the function is increasing. Okay, and then what do we mean? What do I mean by that? It is dy by dx is greater than 0. That's what we mean. Okay. So when you take any point here and you find the gradient and substitute that point in that, if it is greater than 0, that is, if the number is positive, then the function is increasing at that point. Yeah. Similarly, the gradient of the tangent is negative and the function is decreasing. Yeah. That is dy by dx is less than 0. That's its negative. Yeah. And when it is stationary, when the gradient, that is, when you draw a tangent at this point, when this tangent is parallel to the x-axis, that means the gradient is 0. Yeah. So any point you take on this line, any point you take on this line, the slope m is going to be 0. Yeah. And the slope, similarly for any point on this line, the slope m is going to be 0. So therefore, the gradient at this point should be 0, isn't it? So dy by dx is 0. A line parallel to x-axis. Yeah, because there's no change in y value. Yeah. Okay. So in each case, the gradient has to pass through 0. So the gradient here, when you're moving from left to right, the gradient is negative, 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 0, positive, 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 0, negative, 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 negative. Okay, so that's what's happening here. So when you move from the gradient of the tangent to the curve at this point is 0, minimum is 0, maximum 0. That is at both the turning points, the gradient is 0. So what's happening here? At turning points, the curve is said to be stationary, and we can find where these points occur by solving the gradient dy by dx is equal to 0. So we therefore refer to this point as stationary point too, because it is 0, it is stationary. Yeah. Good example is the speed of a car. Yeah. Or when you throw a ball up, it falls back. So the ball, you throw a ball up, goes as a projectile, it takes a parabola up, 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 and then it reaches the maximum point, the stationary point, where it is, the velocity is 0, and then it falls down. Okay. So that is a very good example to understand what is stationary point where the gradient is 0. Velocity in throwing the ball, the speed is 0, because if you plot a graph between distance and time, so that's how it looks. That is time, this is distance. So you're going to throw a ball and it's going to fall down. So if you draw a gradient at this point, that is change in, okay, let me take this as x. Okay, change in distance over time. Okay, change in distance over time will be 0. That's the stationary point. That's the velocity at this point is 0. Yeah. Okay. So stationary points are where the gradient of the function is 0. Okay. At the stationary point, the gradient dy by dx is 0, or y prime is 0. To find the coordinates of where the stationary points occur, first you need to differentiate the function to give the gradient function. Then you have to find the values of x where the gradient is 0, gradient of the function is 0. Okay. Then substitute each value of x where the gradient is 0 back into the original function, that is f of x. This f of x, okay? That is f of x, yeah? and then find the corresponding value of y. Okay. So let's do an example to understand whatever we have covered so far, okay? Because it's just theory won't help us. So let's do an example to understand the whole thing, yeah? Okay, the question now is find the coordinates of the stationary point on the curve y is equal to f of x, where f of x is equal to x squared minus 4x plus 7. So what do we do? First, differentiate the function. So you get 2x minus 4 because and plus 7. The differentiation of 7 is 0. Differentiation of a constant is 0. So there's nothing there. And then after you differentiate, you know that a stationary point is a point where the gradient is 0. So if you want to find the stationary point, you equate it to 0. 2x minus 4 is equal to 0 and x is equal to 2. Now you know the value of x. You can find the value of y, isn't it? By substituting it in the function. Yeah, substitute the value of y and you get the stationary point. So the stationary point is 2 and 3, 2 comma 3. Yeah. So this is where the curve turns. Okay. Now I want you to pause the video and try this problem. Very good. So what did you do? You first differentiated the function. So 2 times 4 is 8, 8x. Before this, please write this in the form ax to the power of n, which makes it easy for you, okay? So let me write it in this form. Plus 1. Now it's easy to differentiate, okay? So it's 8x minus x to the power of minus 2. Again, differentiation of 1 is 0. Differentiation of a constant is 0. So again, let's use the condition where the stationary point, where at the stationary point, the gradient is 0. So let's use that condition and put this equal to 0. And then you get x is equal to 1 by 2. But you have to find the stationary point. That is, you have to find the coordinates x comma y where the curve turns. It could be maximum or minimum where the curve turns. That's what you have to find. So now you have got the value of x, which is half. Now you have to find the value of y. How will you find that? Substitute in this equation and then find the value of y. Therefore, y is equal to minus 6. Yeah. So you substitute in there and you get the stationary point. Okay, but you've seen that for the parabola, you know that this is like a parabola of the form ax squared plus bx plus c. Yeah, this equation is a quadratic function. You know the shape of this quadratic function and you know that a is positive here. A is equal to 1, isn't it? It's a parabola with a is equal to 1. That means a is positive. A is greater than 0. That means the stationary point has to be a smiley parabola, isn't it? Yeah. That means that if you have a shape of this form, that means the curve should be having a minimum point. That means the stationary point should be minimum. The stationary point should be minimum. Okay. So we know that for problems like this, for parabolas, we know how to identify the stationary point, how to identify the nature of the stationary point. You know how to say that whether the stationary point is minimum or maximum by just looking at the value of a. Yeah, if a is greater than 0, the stationary point must be minimum. If a is less than 0, the stationary point is maximum. So you know that how to identify the nature of the stationary points. But how do we decide if we don't know the shape of the graph? Here you know that the shape of the graph is parabola. What if you don't know the shape of the graph? For example, for this problem, You just solved it. Yeah, you just solved that problem and you found the stationary point. You found the stationary point to be 0.5 and 4. Yeah. How do we do that? What type of stationary point is it? Is it maximum or minimum? So that's where you can use the first derivative to identify the nature of the stationary point. So determining whether the maximum or minimum point, one way to determine whether a turning point is a local maximum or a local minimum is, its nature is to consider the gradient of the curve on either side of the turning point. Just a minute, guys. I have a doubt. Did I write 4 or -6 there? Okay, sorry guys. It is, this value is 4. I don't know why I wrote that as -6. Okay, this is 4. Okay. And that is 4. Okay, sorry guys. Yeah, that's 4. Okay. So let's see how to use the first derivative to identify the nature of the stationary point. Yeah, in problems like that. Yeah. So if we know that that is the maximum point, and we have seen that on the left side of the maximum point, the gradient is positive, and on the side right is negative. So at a maximum point, the gradient changes from positive to negative. That is, as you go up, the gradient becomes positive, positive, then maximum, then it starts becoming negative. The gradient is minimum, and it's going to be negative, negative, minimum, and then positive. So at a minimum point, the gradient changes from negative to positive. So you go like this, it's a negative gradient. Then it is 0, the gradient is 0 at the minimum point. Then the gradient starts increasing. So the gradient starts increasing, the gradient is 0 at the maximum point, and then the gradient starts decreasing. That's beautiful, isn't it? Okay, so after you find the turning point, you can consider some values on the x on either side of the turning point to check whether the turning point is maximum. If you substitute a point and see whether if the gradient is positive on the left side and then it is negative on the right, that is, it changes from positive to negative, then it's maximum. And if the gradient changes from negative to positive, it is minimum. Let's do an example to understand that. Yeah. So let's take the same curve. You differentiate it for the first time. So it's the first derivative. And then you take any point. So first let's substitute. We know that this is a point. So let's substitute a point 1/4. Just taking a point on the other side of the stationary point, because you don't know whether because for this curve, you don't know whether this is a maximum or a minimum. So you just randomly take randomly take a point. For example, you have taken 1/4 here, and you substitute it, which is equal to -14. Look at that. This value is negative. So that means, so your gradient is negative. So where is it? So it's negative, and then it's minimum, then it is positive. Yeah. So that means at this point it is negative, and I'm going to take another point which is bigger than this value. So 1 point above this value and 1 point below this value. So below this value we have taken 1/4. So x is equal to 1/4. And above this value we have taken x is equal to 1. So below this value, for x is equal to 1/4, dy by dx is negative. Above this value, x is equal to 1, dy by dx is positive. That means below the value it is negative, the gradient is negative, then the gradient is becoming 0, then the gradient is becoming positive. So what's happening? Negative gradient, 0, positive gradient. So that means it's going to be minimum. So it's something like this, because the gradient goes negative, then negative, the gradient is 0. Gradient means what? The first derivative, okay? The first derivative is negative, the first derivative is 0, and then the first derivative is positive. Therefore, the turning point is minimum. So you have identified the nature of the turning point. Since the gradient changes from negative to positive, the turning point is a minimum point. So you have identified the nature of the minimum point. So how do you identify the nature of a stationary point or a turning point, whether it is a maximum or minimum? Just differentiate it, find the first derivative, find the turning point by putting it equal to dy by dx is equal to 0. Find the turning point just like how we did that before. Then take a point less than that value and greater than that value. Substitute it in the first derivative and check whether it is negative, negative, then 0, then positive. Then it is minimum. If it is the other way, if it is positive, 0 and negative, then it is maximum. We know a turning point occurs for the function at 2, 3. Yeah. To determine whether it is maximum or minimum, we look at the value of the gradient on either side of the point. Okay. So try this out. Pause the video and please try this. Good. So you need to first find the first derivative. Then at x is equal to 1, what is the value? That is 1 point less than 2. So for example, this point is 2, 3, isn't it? That is your turning point. Yeah. So take a point here, 1. For x is equal to 1, substitute it in dy by dx, it is negative. You can see that it is negative. And then take a point on the other side, and you can see that it is positive. Yeah. The gradient is positive. So it's negative. The gradient is negative. The gradient is negative. The gradient is 0. And then the gradient is positive. So it's going to be, gradient is positive. So it's going to be minimum. The stationary point is minimum. Because the gradient changes from negative to positive, the turning point is minimum. Although you can, for a parabola, it is easy to identify, but this is how you can show it using the first derivative. This is useful when you do not know the shape of the curve. Yeah. Here we know the shape of the curve, but previous problem we didn't know the shape of the curve. So it is useful to identify the nature of the stationary point using the first derivative. Okay, now let's see how to use the second derivative to identify the nature of the stationary point. So this is an alternative way to identify the nature of the stationary point. Okay. So what we do here, we take the second derivative of the original function, that is d square y by dx square. That means you differentiate the first time and then you differentiate it once again. So you can either represent it as d square y by dx square, or y double prime or f double prime, f of x double prime, yeah? Then if the second derivative is less than 0 at the turning point, it is maximum. And if it is greater than 0 at the turning point, it is minimum. So this is the condition you're going to use to identify the nature of the turning point using second derivative. Okay, guys, that's important, yeah? So that is the condition you use to identify the nature of the turning point. So let's do an example. Let's take the same example for the parabola, which we did now. We have found the first derivative. Then you differentiate it for the second time. That is, you find the second derivative and you get 2. Now we have to see whether the second derivative is at the stationary point is positive. Yeah. Since the second derivative is positive for all values of x, the stationary point is going to be minimum. So in this example, the second derivative is always positive. Why? Because the function is quadratic. You see, a is positive. A is greater than 0. A is 1. That is why it has always got a minimum turning point. That's why you get it of this form. Yeah. Now, I want you to try this problem. Pause the video, find the second derivative and check whether the gradient, the curve has a stationary point which is minimum or maximum. Yeah, try to identify the nature, whether it is minimum or maximum. Excellent, guys. So the first derivative, you know the stationary point, 1 by 2, comma 4. Find the second derivative at the stationary point, substitute the value at the stationary point, and you see that this is greater than 0. So if the second derivative is greater than 0, the stationary point is minimum. Okay. So 8 to the 16, I will do that for you. 16 plus 8 is 32. So this is, please write this value. Okay. 32 is greater than 0. So the stationary point is minimum. Got it? Okay. Now let's use differentiation as a tool for solving optimization problems. Okay. We have seen that in week 9, we have used linear programming as a tool for solving optimization problems. Yes, that is, our function was always linear. Yeah, in that case, so we used it to find the maximum value, the minimum values, like maximum profit, minimum loss. We've used to solve such optimization problems using linear programming. Now we're going to see how to use differentiation as a tool to solve the maximum and minimum values. Okay, but for any form of functions. Now we are not sticking on to linear function. So the idea is not to draw a graph, that is to avoid drawing a graph and solving the problem using differentiation as optimization tool. So it saves our time and it's much easier to differentiate than compared to drawing a graph. Yeah. So now let's use this differentiation as an optimization tool. Okay, so our example, first example is a large open tank in the shape of a cuboid is made from the sheet metal and has a height and width of x meters and a length of y meters. Okay, these are the dimensions. Okay, so you have the length. I'm just taking this as length, that's breadth, and oh no, y is given as length. So let me take it as given in the question. Okay. So that's height. Okay, sorry guys, height, and that is the width. Okay, so height, width, and length. And it's given that the area of the metal used is 54 meters square. So the problem is first to find an equation for the volume. You have to find the equation for the volume in terms of x. Then you have to determine the value of x for which the volume is maximum. And then you have to find the maximum volume itself. Okay, so let's do that. So what is given? We are given the area, and we have to find an equation for the volume in terms of x. Then we have to find the value of x for which the volume is maximum, and then maximum volume. Let's do that. Okay, so first, what is the volume? Volume of a cuboid is, that's your length, that's your width, that's your height. Volume is equal to length into height into width. Okay, so that means it becomes x times y. So x square y. What about the area? To find the total surface area, we have to find the area of each face. So that's going to be x square for this face. This face is going to be xy, and the bottom face is going to be xy. This face is going to be x squared. This face is going to be xy. That's going to be xy. So we have 2x square. So 1x square, 2x square, and then we have 1, 2, 3, and then we have this face also. It's x, 4, 3xy. Yeah. Did I use that? 1, 2. Oh, I've already done that. Sorry, guys. So 1, 2, 3. Yeah. Okay. So hence 54 maximum area is, you substitute 54 there, and then you get y is equal to 18 over x minus 2 by 3x. And then v is equal to x square y. Put the term, substitute this y into this, and then you get an equation for the volume. The second thing is to find the value of y for which the volume is maximum. And so how do you find the maximum volume? You can differentiate it. First derivative will help you find the volume. So we have to find f prime x, the first derivative. Okay, this is what is your task. So find the first derivative, and you get 18 minus 2x squared. And to see whether it is a maximum or minimum value, you have to do the second derivative and substitute the stationary point. So first, let's find the stationary point. So how to find the stationary point? By substituting f prime x is equal to 0. And then you get the value of x, that is your x value. And then you substitute this value in the function itself here. Here, x is equal to here to find the y. Yeah. Okay. The -3, you can't take it because volume cannot be negative. Yeah. So just ignore that and tell us the reason why you ignored it, because it's negative and volume cannot be negative. Now you substitute x is equal to 3 in this and you get the value of y. So you get the two point, you get the point, you get the two values x and y. And then you find the second derivative and you see that it is negative, so it's maximum. Then substitute the value, find the volume for that stationary point. So the maximum volume is 36 meter cube. Okay. So when you have problems like that, you first write down what is given to you and then form an equation for that. Because it's been asked to write the equation of the volume in terms of x, so you write in terms of x, and when you have the function, because you have to find the stationary point, you first differentiate it. At stationary point, the first differentiation is equal to 0. To find the value of x, that's the best way. Put it as 0 and then find the value of the stationary point. To find the point, put the value of x is equal to 3 there, for which y, yeah, if you want to find the point, yeah. But here the question is to find the maximum volume at that point. So that's why we have to substitute this value here, and to show whether it is a maximum or minimum value, just prove whether the second derivative is less than 0. That's it. Okay, so you have shown that it is minus 12 and so it's maximum. Okay, now over to you guys. I want you to plot this graph using Desmos and see how the graph looks. And it will look like this, but I want you to try it on Desmos. So that is the stationary point. Yeah, you can't take this as your stationary point because volume cannot be negative. So at the stationary point, the second derivative is negative. That is why the volume is maximum there. Any point on this side between 0 and the maximum point, the first derivative is going to be positive, and any point on this side will be negative. And the first derivative at this point, a, will be 0, isn't it? Yeah, that is, you just have to substitute a point here, yeah, in the first derivative. Okay, so if I substitute, for example, let me take 1, yeah, 1, yeah. If I take 1 for x at x is equal to 1, x is equal to 1 is on this side of the stationary point. So then f prime x will become 18 minus 2 is equal to positive. Okay, that means any point you take, you can try another point, any point you take on this side, it's going to be, the first derivative is going to be positive. You take a point on this side, let me take 0.4. Substitute 0.4 there. So you get 18 minus 4. 4 is 16, 16 2 is 32. So it's going to be minus 14. Yeah, it is negative. The first derivative or the gradient is negative. So what's happening? The gradient changes from positive to negative. So it's going to be something like this, 0 and then negative. That is positive. The gradient is positive, 0 and then negative. So that means this is going to be the maximum value. The stationary point or the turning point is going to be maximum. Okay. Okay, now I want you to try this problem and send it by email to me. I'm just giving you a clue here. To solve this, you need to form an equation using the constraint that all the sides add up to 24 meter. Then use it to eliminate a variable in the equation of the area and then differentiate. And then solve this problem. And please send it by email to me. So here you have to find the equation of the volume of the box and then determine the volume of the box when it's maximum and consider that, confirm that it is maximum. Okay, just like the one example we did. Yeah. Okay, so what we have seen now, we've seen how to find the stationary points, how to use first derivative and second derivative to identify the nature of the stationary points. And you have also seen how to use differentiation to solve optimization problem. That's all for now. See you guys.